Let's work through an example of computing the surface area of the surface M, shown here. The surface M is the graph of the function 9 minus x squared minus y squared, and it's the portion of the graph that lives above the xy plane, which is where z is greater than or equal to 0. The method that we're going to use to compute the surface area is we're going to compute this specific double integral. Now, the r in this formula is referring to a parameterization of this surface. Now, because it's the graph of a function, we have the standard graph parameterization. So r of xy is, well, we need the x, y, and z coordinates. So we can just take the x and y coordinates to be x and y, and then z equals 9 minus x squared minus y squared. So this parameterization is available to us whenever our surface is the graph of one coordinate as a function of the other two. Now, what's the domain of the parameterization? Well, it's the shadow of the surface in the xy plane, which is shown in the solid blue. Okay, so let's call the domain D, and it occurs when, in fact, z is equal to 0. And so I get x squared plus y squared is less than or equal to 9. So the boundary is this circle, which is the intersection of the surface when z equals 0, and I get x squared plus y squared equals 9. And then because I have the shadow here, I want all the points inside the unit circle, so I really have the unit disk. I'm sorry, not the unit disk, with a disk of radius 3, because it's x squared plus y squared equals 9. Okay, so then we can work through what rx cross ry is, but it'll be the same thing every time. And so there's probably a place to just have this formula memorized. So rx cross ry, the magnitude of that vector is going to be the square root of 1 plus, and then the partial derivative of this function with respect to x squared, and then plus the partial derivative with respect to y squared. So the partial with respect to x is negative 2x, and the partial with respect to y is negative 2y. And so simplifying, we get the square root of 1 plus 4 times x squared plus y squared. Okay, so this is a scalar function of the two parameters x and y, and so we're going to integrate that function dA over the domain of the parameterization. So we have the integral over d of the square root of 1 plus 4 times x squared plus y squared dA. All right, so that's really the new method that we're learning, is to use this certain double integral to compute surface areas. All right, from this point out, we just have a double integral to compute using whatever methods we've developed so far. In this case, because our domain has radial symmetry and our function looks like it's really a function of the polar coordinate r, we should just switch over to polar coordinates. And so the domain D in polar coordinates, the r values go from 0 to 3, and theta goes from 0 to 2 pi, since we have the entire disk all the way around. This function becomes the square root of 1 plus 4 times r squared, and then dA is r times dr d theta. Okay, so now we just have to compute. So the theta portion of this, because this function is just dependent on r, is going to give me 2 pi. And then the antiderivative of this function is 1 plus 4r squared to the 3 halves, and then times 2/3. And to account for this, here I have an r, but if I took the derivative here, I would get an 8r. So I have to multiply by 1/8. And then we're going to evaluate this from 0 to 3. So what do we get? So the 2 pi combined with this, I end up with pi over 6. And then 1 plus 4r squared. When I plug in r equals 3, I get 3 squared is 9, times 4 is 36, plus 1 is 37. to the 3 halves, and then minus, and when I plug in 0, this is 1, and 1 to any power is 1, so I just get 37 to the 3 halves minus 1 times pi over 6. So that's the surface area of this surface M, and again, our method to compute it was to use a parameterization of the surface, in this case the graph parameterization, and then to compute the magnitude of this normal vector, which plays a role akin to the Jacobian for a change of variables. And so we get the scalar function in terms of the two parameters, and that's what we integrated dA over the domain of the parameterization.